in. Wash your hand, wash your hand, wash your hand, wash your hand. Granny said to wash your hand. Granny said to wash your hand. Before you sit at the table, wash your hand. Before you touch them utensils, wash your hand. 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 Granny said to wash your hand. Granny said to wash your hand. Preparing food and the touching money. Public health is in grave jeopardy. Universally, such dirty practices we can no longer ignore. An ounce of prevention is better than cure. Wash your hand, wash your hand, wash your hand, wash your hand. Granny said to wash your hand. Granny said to wash your hand. You're fixing food, honey, wash your hand. Once you touch the money, wash your hand. Wash your hand, wash your hand, wash your hand, wash your hand.
Good morning, everyone. I am Miss Shallow, and today we will be doing some chemistry. Now, that video that you just saw, it was not a paid advertisement from the Ministry of Health reminding us of how to keep safe in the COVID pandemic, but it was the introduction to my lesson today. Can anybody tell me what they think today's lesson is all about? No, we're not going to just talk about washing hands. Today we're going to be talking about soap. Soap is a chemical compound. The use of soap is chemistry. So in today's lesson, we will be talking about how soaps are made. We will describe how soaps work, and we will also develop an appreciation of the importance of using soap to destroy COVID-19 as the world faces this pandemic. So let's get started. Have you ever read the ingredients on a bar of soap? I have some Irish Spring here with me. Let's see what it says. Ingredients. First ingredient, soap. Well, of course, soap should be made of soap. But it says sodium tallowate and or sodium palmate, sodium cocoate and or sodium palm carbonate. Sodium we're a little bit familiar with in chemistry. We all know sodium as a metal. But have you ever heard about tallowate or palmate or cocoate? What do those words sound like? Does anybody know? Well, tallowate comes from the word tallow, and palmate comes from the word palm. What about cocoate? Not just cocoa, but coconut. What is tallow? Now, tallow is animal fat, okay, fat from animals. Palmate comes from palm, and as we know, palm is a tree, and also coconut comes from a tree. So palm and coconut are plants. But what does a palm and a coconut tree have in common? Yes, we can get oils from both of them. So essentially our soap is being made from oils. Fats and oils contain chemical compounds that are called esters, and these esters are what is used in the production of soap. Now, before we can go into exactly how soap is produced, we're going to backtrack a little bit about esters. Now, an ester is formed from the reaction of an alkanoic acid and an alcohol. Okay? So the alkanoic acid reacts with the alcohol. The molecules are joined together to give us a new compound that is called the ester. And that is what we're finding in our soaps and oils. Now, to join the molecules, we remove a small molecule, namely water. And this type of reaction, where we join the alkanoic acid and the alcohol to produce the ester, is called condensation. So it is a condensation reaction. Now the same way we can take an alkanoic acid and an alcohol and join them together to create an ester, we can take that ester and break it back down into the alkanoic acid and the alcohol. So we can take our ester and we can break that ester back down into our alkanoic acid and our alcohol. It is essentially the reverse of the condensation reaction. Now this reaction, where we're going to break down our ester back into the alkanoic acid and the alcohol, does the opposite. To join the molecules, we were removing water. To break it down now, we're going to be adding water. So we're adding water to the ester to break back down the ester into the components. Now this type of reaction is called hydrolysis. And the name of the reaction tells you something about it. Hydro here comes from water, lysis comes from splitting. So the word hydrolysis essentially means to split using water. Now there are two types of hydrolysis that esters can undergo. We have acid hydrolysis and we have alkaline hydrolysis. What do you think is the difference between the two? Right, one involves an acid and the other one involves an alkaline. Now in the acid hydrolysis, the acid is simply used as a catalyst. Does anybody remember what a catalyst is? Very good. A catalyst is a compound that is used to speed up the rate of the reaction, but it does not involve itself in the reaction itself. It does not participate in the reaction, but simply speeds up the rate of the reaction. In the alkaline hydrolysis, however, the alkaline becomes a part of the reaction. So, we have the ester reacting with an alkaline, and that's going to give us back our alkanoic acid and our alcohol. But like I said, in the alkaline hydrolysis, the alkaline acts as a reactant. Remember, the point of hydrolysis is to break down the ester back into its component. But Mr. De Silva taught us something very important in the last lesson. He looked at the reactions of acids and alkaline. Does anybody remember what Mr. De Silva said? Very good. The alkaline will always react with the acid to produce a compound that is called a salt. That salt that is made during the alkaline hydrolysis, where the alkaline essentially reacts with the alkanoic acid that is formed, is what is our soap. So the soap that we're using is made from the alkaline hydrolysis of our esters. We can summarize that equation very simply. Okay? So when we have our fat or oil, which is our ester, we react that with an alkaline such as sodium hydroxide. We're going to heat that. We end up with a salt of the long chain acid, and that salt is our soap. And we also end up with an alcohol. That alcohol is glycerol. That process is called saponification. So essentially, saponification is the process by which soaps are made, and the chemical reaction involved in saponification is the alkaline hydrolysis of large esters. Today we're going to actually make some soap. You would be surprised at how easy it is to make soap. And the process has been the same throughout history. What would we need? Of course, we need some sort of fat or oil. Today, I would be using coconut oil. I love coconut oil. Of course, we also need our alkaline, and today we're going to be using some sodium hydroxide solution. I must let you know though, that when we are preparing soaps, we have to use a concentrated form of the alkaline. We tend to use at least 5 mole per dm cube. We would also need some supersaturated sodium chloride solution. If you look at the bottom of my beaker, you can still see some salt in it that tells you that my solution is super saturated. So let's get this going. Now the first thing we will do, we will measure out about 15 mils in my measuring cylinder of my coconut oil. And remember, when measuring, we always place on a flat surface and we go down and read at eye level at the meniscus. So let's see. Very good. We're going to take that and we pour it into a beaker. So 15 of my coconut oil. And you can use whatever fat or oil you choose. Like on our Irish Spring, they used palm oil as well. Then we're going to measure 20 cm cube of our sodium hydroxide solution. And we add that to our oil. Now we have to heat. So we are going to light our Bunsen burner and we are going to heat gently. Now while this is heating, we're going to have to stir, and you can already see that my mixture is turning white. And it's turning white as our sodium hydroxide begins to react with our ester in our oil. Let's adjust this flame a little. Right. Now you do this for about 20 to 30 minutes. The length of time would depend on how concentrated your alkali solution is or the type of oil that you're using. Okay, so we continue to stir and we heat, and as we're heating, soap molecules begin to form within our beaker. Now, like I said, this takes quite a while, so you stir and allow it to form. Now you can already see some white suspensions in my mixture, and that is my soap beginning to form. This takes a very, very long time, so you have to be patient. I hope you appreciate the effort that goes into making the soap that we use every day. Now, unfortunately, we can't stay here for half an hour stirring, so I made some for you already. So let's just take this off. There we go. And this is what it looks like after the 30 minutes, okay? Notice it's thick. If you look at this one, we can just see a tad of the soap forming on top there. So after about 30 minutes, you're going to get a thick paste. Now when you remove it from the Bunsen, you allow it to cool, but not cool completely. And then to that, you add your sodium chloride solution. Now the reason you're adding your sodium chloride solution is to help this soap to precipitate out of the mixture that you are heating. Once you do that, you're going to filter to remove your soap. So of course, we will need our filter paper, which we will fold. I hope you remember how to fold filter paper. So you fold it in half, then you fold it in half again, and then you open one of the flaps. Right? We're going to moisten this filter paper very quickly. So we moisten the filter paper, place it in our funnel. We're going to use a conical flask, and then we are going to filter our mixture. We're filtering to remove all of the excess liquid and allow us to collect our soap. Now, once you have finished filtering, you can get creative with your soap. You can add color, make it a pink soap, a blue soap, a green soap, or you can even add a few drops of essential oils to give your soap a fragrance. You're gonna make it yours. So we're filtering, and I still have a few drops left there, but I want to show you what our soap would look like. See that? Looks like soap. Now it's still wet. What you can also do, after you've added your color and your fragrance, you can put this in a mold and make it any particular shape you want. I like seashells, so I'd probably put this in a seashell mold and make a nice little seashell shaped soap. Now we have to test our soap. Science is about testing things and seeing if they work. So we're going to test our soap to make sure it works. Now take our soap, and we're going to put it in a boiling tube, and we're going to add some distilled water to see if our soap works. How do you think we would know if our soap is going to work? Right, it must lather, it must look like soap. So we shake vigorously, because with soap we have to have some sort of agitation. And let's see if we're getting you see that? Bubbles. So our soap is actually working. So you can make soap at home, very simple, very easy. All you need is some oil and some alkali. Now you may say, I don't know exactly where I will get alkali. Believe it or not, you can get alkali from things that you have in your homes all the time. Banana skins, for example, plantain skins. Banana skins and plantain skins have a high concentration of potassium hydroxide, which is an alkali. What you can do, you can collect these skins, dry them, and then burn them. The ash, you can then soak that in water for a few days, and then you can use that as your alkaline solution. Believe it or not, that is how they make the African black soap. I know many of us know the African black soap that does wonders to the skin. The ash in particular has other properties that are good for your skin. So if you can't get laboratory sodium hydroxide like I use, you could probably get some from some old banana skins and some plantain peels. Great. So now we know how soap works. Well, sorry, how soap is made. We're going to go into exactly how soap work. Now to do that, I want to show you a chemical reaction that can be used to make soap. Now remember that soap is created by the alkaline hydrolysis of large esters. So let's say we have a large ester. I will use octadecanoate, so that would be C17H35 COO, all of that, 3C3H5, and we're going to react that with sodium hydroxide. And of course, we know we're going to get a salt. Remember, the alkali, sodium hydroxide, would react with the alkanoic acid that is formed during the hydrolysis, and we get a soap. So it would be C17H35 COONA plus our alcohol, which would be glycerol, C3H5OH3. Okay? So this is our ester, this is our alkali, this of course is our salt, but that salt is what we know as soap, and this here is our alcohol. So if we're to look at the structure of the soap molecule, we can draw that out. So let's go. Carbon there would have a double bond to the oxygen, and another bond to the oxygen there bonded to sodium. Now, because we have a salt here made from an alkali and an acid, of course, it's going to be ionic, okay? And then we have to go in and put in this long chain. Now, you could imagine drawing out 18 carbons going down there and then filling in all of those hydrogens. That is quite a lot of work. So instead of doing that, we can actually simplify the diagram of the soap by drawing a head, which represents this ionic portion, and then a tail, which represents this hydrocarbon portion. Okay, so the soap molecule can be simplified using that structure. Now this here is our head, and this portion is our tail, almost like a kite, right? Now the head portion is what contains our sodium, so this head is ionic, and our tail there would be our hydrocarbon chain. Now because our head is ionic, it is going to be polar. Polar substances are ionic. So another point to note here is that it is polar. And because it is polar, just like water, that portion is going to be water-loving. It's going to be able to dissolve in water. The term we use for that is hydro from the water, philic. Okay, hydro from the water, philic there to say that it's like. One of the things that I always do in trying to remember these, I remember hydrophilic has an L. L for like. Then we have our hydrocarbon tail here. Now remember, this is just hydrocarbon, so it's not ionic, right? Just carbons and hydrogen. So this end is going to be non-polar. And because this end is non-polar, it is not going to dissolve in water. We have to remember our solubility rules. Like dissolves like. Okay, water is a polar molecule, and this region is non-polar. And because it is non-polar, it doesn't like water. And the term we use to describe that is hydrophobic. Okay, again, hydro from water, phobic comes from what word? Phobia. And what does phobia mean again? Affair. So this portion doesn't like water. So how soap works is directly related to the structure. Remember, in chemistry and in our sciences, function is always related to the structure. So we know that the soap molecule essentially has a hydrophilic polar ionic head and a hydrophobic non-polar hydrocarbon chain. So let's look at how soap works there. Right, so soap we know is used for cleaning, and right now in this pandemic they're always advising you wash with soap and water. It's better than using sanitizer. We only revert to the sanitizer when we don't have soap and water. So how exactly does the soap work? Now remember, the soap molecule has two main parts, the hydrophilic head and the hydrophobic tail. Now dirt and oil and grime that can be on any surface is also non-polar. And again, we have to remember the solubility rules. Like dissolves like. So the non-polar tail of the soap molecule likes the dirt. It attaches to the dirt, it binds to the dirt. And the polar head, the ionic polar head, likes water. So what happens is that the tail of the soap molecule binds to the dirt and oil and grime. And the polar head that is going to be dissolving in the water allows it to actually be lifted off of the surface. So as you can see, the tail attaches to the dirt and grime, the polar heads are sticking out, and those would be lifted up by the water and be washed away with some agitation. Okay? Now, we're currently facing COVID pandemic, and we're constantly hearing, wash your hands, use soap and water. How does soap and water help with COVID? Well, we have to look at how soaps are actually able to destroy viruses. So let's look at that. Good. Now, a virus essentially is DNA enclosed in some sort of capsule. The COVID virus has a capsule or membrane that is made from lipid. What are lipids? Right, lipids are fats. And what do we know about fats? Fats are non-polar. So when you wash with soap, if let's say there's a COVID virus on a surface or whether your hand or something, and you wash it with soap, the hydrocarbon tail of the soap molecule is going to attach to those lipids in the membrane of the virus. And when it attaches to the lipid membrane, it essentially will pry the membrane apart. So it's essentially ripping the virus apart. Once the virus is broken up, those tails again will surround the virus particles, and with the hydrophilic head, surround it in a bubble, and that will be easily washed away. So soap and water is very effective in fighting the spread of COVID because soap literally rips the virus molecule apart, and once it is ripped apart, it is going to be simply washed away. So today we learned a lot about soap. We learned how soap is made. We learned that the process is called saponification, and we essentially use a reaction, it's the alkaline hydrolysis of large esters to create soap. Soaps can be made very simply at home as long as you have the necessary materials, which would be an ester, so some fat and oil, as well as an alkaline. But remember, the alkaline must be concentrated. Again, if you cannot get access to laboratory alkaline like I use today, you can make some at home, maybe using banana skins or plantain skins. We also looked at the structure of the soap molecule, and we said that the soap molecule has two main parts. It has a hydrophilic ionic head that is water-loving, and a hydrophobic non-polar hydrocarbon chain that doesn't like water. And it is this structure that allows soap to clean, because that hydrophobic tail will attach to a dirt or grime or even viruses, and then the hydrophilic head would allow those to be lifted from the surface. So let's get some questions to see how much you would have learned. I'm going to erase the board because I don't want anybody cheating, looking at the answers on the board. Right, let's go. First question. Which of the following is the process by which soap is made? Is it A, esterification, B, condensation, C, saponification, or D, acid hydrolysis? Okay, I know you know, so yes, what's the answer? The answer there is C, saponification. Very good. Next question. Which of the following chemical reactions result in the formation of soap? Is it A, the alkaline hydrolysis of large esters, or B, the acid hydrolysis of large esters? What about C, the condensation of acids and alcohols, or D, the alkaline hydrolysis of short-chained esters? Yes, the answer is A, the alkaline hydrolysis of large esters. And remember, these large esters can be found in our fats and oils. Question 3. Which of the following would best represent the pH of a soap? So which of the following would best represent the pH of a soap? Is it A, 3, B, 10, C, 7, or D, 1? Ah, correct. The answer is B, pH 10. Because remember, on the pH scale, anything over 10 is alkaline, and the soaps are made using the alkaline hydrolysis. Question 4. Which of the following best describes the structure of a soap molecule? Now, this is a tricky question because of all of the combinations. So let's read it carefully to see what is our best answer. So it says a hydrophobic polar head and a hydrophilic non-polar tail. B, a hydrophilic polar head and a hydrophobic non-polar tail. C, a hydrophobic non-polar head and a hydrophilic polar tail. And D, hydrophobic non-polar head and a hydrophobic polar tail. Let's look at those options very carefully before we decide on the answer. So what's the answer? Right, the answer would be B, a hydrophilic polar head and a hydrophobic non-polar tail. If it is hydrophilic, it must be polar because it's going to be water loving. And if it is hydrophobic, it's going to be non-polar. Thank you for tuning in today. It was a pleasure being here with you. See you in the next lesson. Remember, be safe, wash your hands with soap and water, and stop the spread of COVID-19. Always look for the science in our everyday activities. Thank you and see you again.